Assalamu alaikum. Before starting Y and delta, first let us recap what are the conditions for having two elements in series. What are the conditions? If those are fulfilled, we can call these two elements or three elements are in series. And what are the conditions for elements to call themselves in parallel? Okay, so in order to have two elements in series, let me make this pens bigger. Okay, so in order to have two elements or more than two elements in series, let's have two example, two in series, we need to have one node common between two elements. So instead of elements, let's call register for simplicity. So let's call this is R1 and R2. So if this is node A, let me change the color. If this is node A and this one is node B and node C, so we have this node B which is exclusively shared between R1 and R2. That means B does not have any other element connected to it. So we can call that R1 and R2 are in series. So these are the conditions we have. In order to call R1 and R2 in series, we need to have two conditions fulfilled. First of all, they should have only one node between them. That means they should have only one node in common with them, and this common node should not be shared with anyone. That means this node should be exclusively shared between them. Now time for parallel. If we have, let's say, two resistors like in this fashion, sorry for the bad drawing. So if this is node X and this is node Y, so let's call it this is R3 and R4. So we see that both R3 and R4 have these two nodes in common. That means we have this X and Y. In between we have R3, and we also have this R4 that is in between node X and node Y. In that case, we can call this R3 and R4 are in parallel. The problem arises when this kind of circuits are there. For example, let's have two elements are in series. They have only one node in common, that is node B. Just following our previous example, that is node B, and in this side we have node A, and in this side we have node C. So these two are in series, right? So R1 and R2. Now if we have another element that is connected in node B, so let's say we have not this, let's say we have another node which is node D, and let's call it R5. Can we call that R1 and R2 in series? No, we can no longer say that because this node B is not exclusively shared. Can we call that R1 and R5 in series? No, still we cannot say that because R1 and R5 have that this node B is in common, but this node B is connected to R2. So okay, let's try the last one. Is R2 and R5 in series? No, it's not, because they are not in series because this node B is shared. So we cannot call this kind of circuits as series or in parallel circuits. So we cannot call that. Definitely these are not parallel, because we do not, in order to have parallel, we have both of these nodes common. We do not have any resistors here like R1, R2 and R5. None of them have both of these nodes common together. So this is one special kind of circuit. You see, this is not neither series nor parallel. This is one special kind of circuit. So this kind of circuit has a special name that is called, it's a Y circuit, or it looks like a T, right? The English letter T, capital T. So capital T. So it looks like a T. So since it looks like a T, we call it a T circuit, like T, as in the capital letter T. So this T has three resistors connected to each of its arms. So this is a T circuit, or we can call it a Y circuit, because if you try to bend these two arms of T, electrically it will remain the same circuit, but now it looks like another English letter that is known as Y. So this is Y. So we pronounce it, we write it like WYEY for pronunciation, but this is the, we call this kind of circuit as Y circuit. So Y, that means the English letter Y, capital letter Y, and each of these arms of this Y have one resistors connected to it. So this kind of circuit are known as Y circuit or T circuit. This is exactly the same thing. Y or T are the same circuit, same thing. So this is one example of Y circuit. Okay. uh, just for a side note, you see that this kind of Y circuits have a common point. They have all these three elements have one common node. So let's call it N. It's a neutral point. We call it N. Okay, so every Y circuit or T circuit, we refer it to, I personally refer it to Y, or in our book they have also referred it as Y instead of T, but you should also know that T is the same as Y. Okay, so Y or T, whatever you call it, they should have a common node that is shared between all the three elements. Those are known as N, or neutral point or something. So here this node B is the neutral point. This node B will be our neutral point because this node B is connected to R1, R2 and R5. All three of them are connected to node B. So this is called a Y circuit. Now it's time for delta. What is delta? Okay. You have already got a hint that these Y and delta came from the shapes of these letters. So the Greek letter delta looks like a upside down triangle like this. So if you have all these arms, that means three arms of this upside down triangle as resistors, then you have a delta circuit. So a delta circuit looks something like this. So this one, and let me erase this too first. So we can call this is a delta circuit, but this is obviously not a full delta circuit because it's all these three elements are in series, but it's not actually a circuit, but still you get the idea. So let's take a look at the real delta circuit. How does it look like? So let's take an example. Let's take both of them. So you see that there are three resistors, RA, RB and RC. All these three are connected as if they are connected in a triangular fashion, and they have, it looks like they are in series with each other. All these three elements are in series with each other, but in reality they are not in series. We call this kind of circuits as delta circuits. You see that this is node, if you want to denote it as node, so this is node 1 node, so 2 and 4 are the same nodes. So if this is node 1 and this is node 3, so we have three different nodes over here. So RB is in between node, let's for the sake of simplicity let's call it node A, node B and node C. So RB is in between node A and C. So here RB is also in between node A and C. Sorry, I have to mark it as node C. So this is node C and this is node A. Node B. So here these two circuits are exactly the same circuit because electrically there is no difference. No, RB is in between A and C. RB is in between A and C. RA is in between B and C. RA is in between B and C in this figure. RC is in between A and B. RC is also in between A and B. So for such reason we can call this circuit is exactly same as the previous one, or they can interchangeably used. So these kind of circuits are known as delta circuits, or even though it looks somewhat like a delta, this resembles somewhat like a pi, the Greek letter pi. 3.1416 or something. So this is a pi circuit. So delta and pi can be interchangeably used. Delta circuit means the pi circuit. So previously we had t and y, now we have pi and delta. So if we want to couple them together, we call it y and delta. Either use y and delta or use t and pi. In general, we use y and delta more than this t and pi, but you should also know that y is also known as t and delta is also known as pi. Okay, so these are the examples of y and delta circuits. Now let's take a look these two versions of y circuits. Here you can see that we have four different terminals. This is a new concept for you. For example, we have understood node. So this is a node 1, 2, 3, 4. We have 4 nodes here, but here we have 4 different terminals over here. For example, this is terminal 1, terminal 2, terminal 3 and terminal 4. You can how do you call it, you can relate the term terminal as a wire that is coming out from the circuit, something like that. A wire or a cable that came out from the circuit, we can call it a terminal. So we have two terminal 1 and 2 at the left side, and 3 and 4 terminals are at the right side. So you can simplify it like this. This figure A and figure B are the same. So we have a 4 terminal circuit. We have terminal 1 and 2 on the left and terminal 3 and 4 at the right. Here this is a Y circuit, so it will have a common point, this one. So this is the neutral point N. For delta we have something similar. So this is one delta circuit, and the same circuit can be written like this. Here we have also expressed the the delta circuit in terms of terminals. Terminal 1, terminal 2, terminal 3 and terminal 4. Here one common observation is that this delta circuit does not have any neutral point, any common point. It doesn't have any point N. Any neutral point N is not there for delta circuit. So delta does not have any neutral point, but Y has a neutral point. Okay, now our goal is, now we have understood what is delta circuit and what is Y circuit, Y and delta. We can recognize this Y and delta circuits so that we can identify them. So the upper one is Y, so these are Y circuits and these are delta circuits. Our goal is to derive a formula so that if a Y circuit is given, we can convert it to delta, or if a delta circuit is given, we can convert it to Y. This is our goal. Why this kinds of goal will be necessary? Let us, if you remember the previous example, if we have this kind of circuit, we cannot solve them using traditional approaches. So for example, we have a delta at the bottom part. For let's say this is node A. Let's call this node as node A, node B, and no, we already have a B over here. Let's change the notations. Let's call this node as X, this is node Y, and this is node B. So you see that X and B has 30 ohm, X and Y has 20 ohm in between, and B and Y has 50 ohm in between, just like the delta circuit we had earlier. So here we have 3 different elements that are connected to each other. So we can call it X, this is Y, and this is node, let's call it B, node B. So now if we can convert this to Y, We'll see how to convert it later on, but let's say we can convert it to y. So if we try to convert it to y, it will have a neutral point. So let's say this is that neutral point, we call it n. So here you will have from n, let's take a look this one. So in Y circuit you have this n over here. So from this neutral point you have one resistor to each of the nodes. So here we have these three nodes, that X, Y and B. So from the neutral point we should have one resistor to each of the where is the color, to each of the elements. So here we should have one resistor to Y, one resistor to X and one resistor to B. Okay, this is just an example. There are lots of ways to solve this problem. So now it looks like an Y. So here we had a delta, previously it was delta, like this RB is 30, RC is 20 and RA is 50. Now we have converted them to Y, so it should look like something like R1 is this one, so this is R1, this one is R2 and this, the bottom one, is R3. Okay, so if we can successfully do this, we'll learn later on how to do this. So if we want to replace this outer delta to this inner with this inner Y, then we can disconnect this delta from here. So let us delete all this. Sorry, I'll try to make it faster. Oops. Okay, so now it's quite easy to solve this circuit because of this delta to Y transformation, because now you see that this 24 ohm resistor and this R1 resistor are in series because they have this X node that is exclusively shared between R1 and 24. We can also call this is R2, by the way, R2. We can also call this R2 and 10 ohm are in series because we have this Y node, only Y node is common in between, and these two are in series, and this Y node does not have anything that is connected to another element. Okay, so if you want to simplify, then it will become, so 24 plus R1, so it will be something like a resistor that is 24 plus R1 because we can add them together, these two are in series. With this element we also have another element that is 10 plus R2, right? Now what we did is we have added these two elements together and we have added these two elements together. We have made them these two as 1 and these two as 1. So we have written 24 plus R1 and 10 plus R2. And now these two elements are connected to a node that is known as node N. So we write N here. So if this is node N, so this N is connected to both of this element, and rest of the elements of the circuit remains the same as previous one. And from N we have R3 that is connected to N to the node B. Now we have this 240 volt or whatever the value is, that is Vs, which is 240 volt. Okay, so this was 13. So now it's quite easy to solve for I, because now we can write the expression for R equivalent, that means RAB. So this is node A and this one is node B. So the expression for I should be Vs divided by RAB. So what is this RAB? The expression of for RAB would be, see that 13 and these two elements are in parallel. We didn't name this node, so let's call it a Z node. So we have this Z node. In between this Z node and N node, we have this resistor and this resistor, 10 plus R2 and 24 plus R1. These two resistors are in parallel, so we can make them one. So, and this one resistor will be in series with 13 and in series with this R3. So this RAB should be something like 13 plus, so 24 plus R1. We will write a complex expression right now. So 24 plus R1, so 24. Complex doesn't mean mathematically complex, I mean a little bit complex than the previous one. Complicated, let's say, let's not call it complex, because complex means something else. So 24 plus R1 parallel, I'm just writing the expression, I'm not solving this problem. So plus R2, this whole thing is one resistor, that means this whole thing is this one, okay, plus this R3 over here. So this is R3. If you know all the values, now you can calculate the values of I over here. So you see that using delta to Y transformation, we managed to solve this circuit. Can we do the opposite? Can we convert any Y to delta? Answer is yes. Why not? So let us take another example. Copy. Let's paste over here. So no, let me take another one, not that one. Okay, let us take this one instead. This one is better. Okay, so can we make it in our previous example, we made this delta, the lower delta, that means delta consisted of 20, 30 and 50, and we convert it to Y. Now we will do the opposite. Can we make the Y, is there any Y in this circuit, and can we make it a delta? The answer is yes. Why not? So we see that we have a Y over here. Say this Z is our that neutral point. That neutral point is Z, and this Z node has three elements connected to it. So 10, 20 and 50. So here you can spot a Y connection here. So this is a Y. Or we have another Y in this circuit. For example, this one, 24, 20 and 30. These three are also creating a Y. Or this 13, 24 and 10, this is also another Y. So either this problem can be solved in various ways. I will show only one, and the rest of them are self-explanatory. You can follow in the similar fashion. So let's take a look at this 20, 10 and 50. So if we can make these three, if we consider these three as Y and Z as the neutral point, in that case we have the three nodes X, Y and B, and Z is the neutral point. Remember, for a Y, in order to have a Y, you need to have a neutral point. You need to have a neutral point. So in our example, this neutral point Z is called Z, and the upper 2 points, so if we have this one as 10, so this is our node X. If we have this arm as 20, so this is 10, this is 20, so this is node Y, and the bottom is 50, so this is node B. So you see that we have created a Y here. So here and here. So here we can see that there is a y connection is there. So if we can manage to make it a delta, so what it would look like for a delta. If you remember, for a delta, all these three nodes are connected to each other. If you remember, delta circuit looks like, how does a delta circuit looks like? All the elements that are connected to each other, x, y, and the other node b, have all the elements connected to each other. So if you have three elements, they are connected to three different nodes. So let's go back to our example. Say we have this x, y, and b node common to this y circuit. So if you want to change it to delta, what you need to do is to have something like, this is node y, this is node x, and this is node b. So you should have something like one resistor in between x and y. So this is x and this is y. One resistor in between y and b. So another resistor is in between x and b. So it is something like this. So this one, and this one. So when you convert this one, you remove the internal one. Okay, so here we can also make changes like here x to y, there should be one. So x to y, there is one resistor. So y to b, there should be another resistor. So y to b, there is another resistor. And x to y, y to b, so x to b, there should be another resistor. So this is x, this is b. Now when we have successfully replaced them, then we can delete the internal y. So we do not need this y anymore. Now you can see that you can solve this problem quite easily, because now you can say that, let's call it RA, RB, and RC. So RA, RB, and RC. So we have RA in between x and y. So x and y, we have RA. For y and b, we have RB. And x and b, we have RC. Now it's quite obvious. Just like the previous example, we can simplify this, because we have RA and 24 are in parallel, RB and 30 ohm, these two are also in parallel. So, and when you have these two parallel resistors together, these two will be in series, so you can add them together, and the whole thing will be in parallel with RC, and that whole thing will be in series with 13. So the equivalent resistance RAB should be something like, we will not write every part of the equation, we will write the overall final expression. So it will be 13. You have to be able to do this kind of calculations in your head. This is also part of learning. So 13 plus, now we have this parallel RA parallel 24 plus RB parallel 30. So we will write RA parallel 24 plus, because we have these two in series, so RB parallel 30. Since these two are in series, and before that we cannot add this together because we have another parallel element together, so we should write these two are again in parallel with RC. So the overall expression becomes something like this. I know it becomes very complicated, but when you do these kind of problems, it will be much easier, trust me. So this is another way to solve this problem. There are many other ways to solve this. For example, if you want to consider the upward delta over here, so this is 24, 20 and 10, there is a delta, or there is another y over here. So there are many other ways you can solve this problem. See, so now we'll learn the theory. I hope things are clear and we have understood the necessity of y to delta transformation.